we were looking at normal and frictional forces, and just to tie it all together, whenever you have an object that's on a horizontal surface, whether it's resting there or whether it's moving is not really relevant to our discussion, but you have an object which is on a horizontal surface. There are a number of forces that are acting on that object. And in terms of vertical forces, there are only two forces that act on this object. There may as well be horizontal forces, and I'll get to those in a second. But what you have acting on the object is a force due to gravity that acts down. You have a normal force, and the only reason I'm drawing it where I just drew it is so that I could make sure I drew it the same length as the gravitational force. If the object is on a surface, then presumably the object is not moving up or down. It's resting on the surface or moving along the surface. But that means that the vertical forces, the forces that are acting perpendicular to the surface, are balanced. There's a net vertical force here equal to 0. So what does that tell us? It tells us that the gravitational force that acts downwards is equal in magnitude to what we call the normal force acting upward. And again, this may seem picky, but it shows a really good understanding of what's going on. If you were to write this, then that would be incorrect. The normal force is not, and I don't know if you just caught that, but I put a line through the equal sign to make it a correct statement now. The normal force is not equal to the gravitational force. However, the magnitude of the normal force is equal to the magnitude of the gravitational force. So this is the first little lesson from Thursday. If you ever need to know the normal force, you just say to yourself, well, I don't have direct access to calculating a normal force, but what I can do is I can calculate the magnitude of the gravitational force. And gravitational force, of course, is mass times the acceleration due to gravity, or you can call that little g the gravitational field strength. So by calculating the gravitational force, you're really calculating the amount of the normal force. The other thing that so that's how you would do number one, by the way. But what I'm doing here is I'm just doing a review of everything that we learned. The other thing that we learned is that there is this thing called the coefficient of friction, and I'm going to try to film a lab where we can collect data, and you'll have to do the measurements based on the video, but we would have done this lab already. What we would have done is taken a block of wood and put it on a horizontal surface, and I believe I talked about this before. I'm going to add something to my diagram here that if you're writing this diagram down, I don't think you want to add. But on this block of wood would be a hook, and we would attach to the hook a spring scale. This is sometimes called a Newton scale because it's calibrated to measure force in newtons. And then you would apply a force in this direction. There would be an applied force. And we would do our best to drag that block of wood across the floor at a constant speed, which is a very tricky thing. But if you think about that, if I'm moving it at a constant speed, then that means it's not accelerating, so the force that I apply has to be balanced by some other force. And that other force is the force of friction. So what we would actually be measuring indirectly is the force of friction. And we would discover that if we were to calculate, there's lots of ways for me to explain this, but if we were to calculate the magnitude of the normal force and divide that by the magnitude of the force of friction, we would get the same number all the time, assuming we use the same material for a surface and a block of wood. And I'm going to come back to that a little bit later because, again, I think I'm going to try to set up a lab where we actually do this. I think it's a valuable learning experience. So if you did do this lab, I'm just going to clean this up a little bit. if you did complete this lab, whoops, I meant to put force of friction down here. I hope I did earlier, but I may not have. If we calculate the normal force and divide it by the force of friction, I believe I said force of gravity earlier, so I misspoke. You always get the same number. So this thing is found by calculating the magnitude of the force due to gravity. And there's a lot going on here. The reason why we calculate the force due to gravity to find the normal force is because the force due to gravity downwards is exactly equal in magnitude to the normal force upward. So that's what we would do in the lab. The force of friction is the measured applied force. And the reason for that, I suppose I can put in my other forces now. I'm applying a force in this direction. If the block doesn't accelerate in our hypothetical lab, then what that means is there's an equal but opposite force backwards. So what you have for an object moving at a constant velocity along a horizontal surface is the following free body diagram. And the free body diagrams are definitely going to become more complicated as we move on. This free body diagram is very rich with information. It tells you that the magnitude of the gravitational force and the magnitude of the normal force are equal. There is no direct way to calculate the normal force, so you calculate the gravitational force in its place. In the lab, if we're moving this block at a constant velocity, then the force that you apply forward by pulling on it with a spring scale must be exactly equal to the force of friction backwards, because if you were applying a greater force forward, it would accelerate forward, and if you were applying a smaller force forward, you wouldn't be able to move it. So getting back to the review from Thursday, we would discover that this is always going to give you a constant value if you use the same block of wood, the same material for the object and also for the surface. So if we did this experiment with a block of cedar wood on a piece of glass, we would get a particular value for this coefficient of friction. And that's the formula that we use for force of friction. We normally write it slightly differently. Let me reorganize my work here just to give myself a little bit more room. We normally see that force of friction formula written in the following way, that the magnitude of the force of friction is equal to the coefficient of friction multiplied by the magnitude of the normal force. And again, when you use this formula, how do you calculate the normal force? Well, the normal force has a magnitude equal to the force of gravity, so you calculate the force of gravity instead. Even though they're in opposite directions, they have the same sizes. All right, take a look at your work, please. I hope that that was a sufficient review to kind of get those brain cells percolating again. Does anybody have any questions you would like me to go over from this section? It was 1 through 9. No? Okay. If you do have questions, the same thing applies. You know, maybe tomorrow when I say, do you have questions, or later today, when we get started on our next lesson, you can say, you know what, can you go back and show me how to do question 8 from the previous lesson? We can always go back and answer them. But I'm hoping that the fact that there's no questions is a good sign. Tells me that you guys understand the material. So we're going to be moving on now and looking at frictional forces that are on what we call inclined planes. So this is section 20.2.7. Let me pull up the file. This is section 20.2.7, which deals with friction and inclined planes. So we're going to be talking here about calculating 2 things today in this lesson, and then we're doing a second lesson later on this morning as well. So we want to be able to determine the normal and the normal force and the force due to friction on an inclined plane. So I want to make something very clear from the beginning, and if you choose to write this down, it's not a bad idea. I'm going to come back to it and complete it a little bit later. But we have 2 different situations now that we're going to have to grapple with. One of them is when you have a mass on a horizontal surface. And I'll draw that again. It's really the same diagram that I've shown you before. We've got a box there that I'm going to draw on here. And in terms of normal and frictional forces, again, this gets tedious, but these diagrams are going to become more and more complicated as we move on. In terms of vertical forces, I'm not going to put in a force of friction or anything here just yet. We have these 2 forces, the normal force up and the gravitational force down. And as long as we're on a horizontal surface, as long as the surface is horizontal, when we calculate the force due to friction using our formula, what we do for the normal force is we use the force due to gravity instead. This is a very important idea here that I'm talking about. This forms the basis for all force analyses when an object is on a horizontal surface. You use your formula for the force due to friction, but when you go to calculate the normal force, you calculate the gravitational force instead because they are equal in magnitude. Now, what we're learning or going to learn today is what happens when we have a mass on an inclined plane. Now, what is an inclined plane? An inclined plane, everybody, is a ramp. I mean, if you want to use the phrase ramp here, instead of saying, I spelled inclined wrong, so I better fix that. If you want to use the word ramp instead of saying inclined plane, that's up to you. I'll probably use inclined plane most of the time. So what we're talking about here, and again, a reminder, feel free to ask a question in chat, to interrupt me if you need some clarification, to unmute your mic and say something if you want me to stop, because I need to know how I can help you, and I can't see the look in your face that says I'm a little confused. So you have to own up to that and say, you know what, I don't quite get that, explain it to me. And that's what we're here for. So when I draw this, this is entirely different. What we are talking about here is an object on some slope. And typically we draw the inclined plane by drawing a triangle, but you have an object on it, and it doesn't matter how big or small the object is, but it's either at rest on the surface of the plane or it's moving. And it could be moving, and this is going to get very complicated later. This object could be moving up because somebody is pushing it up, or you're pulling it up with a rope, or it could be moving down, and it could be moving down simply because there's not enough friction to hold it in place, or it could be moving down because even though friction is holding it in place, somebody is pushing it down. So there are all kinds of situations that can arise here. But when we take a look at this situation, I'm going to back up. On a horizontal surface, we use this formula to find the force of friction. So we are going to be using that formula to find the force of friction on an inclined plane as well. Except it is not going to be the force due to gravity that we use to calculate the normal force. And that's part of what this lesson is about. Part of what this lesson is about is, well, really pretty much what the lesson is about, is what do we find here so that we can say that's the normal force. The normal force, by the way, is going to be a force acting in this direction. If you were to go back and look at your notes from last week, a normal force always acts perpendicular to the surface. So what you want to do here, and I'm just going to show this to you, but we're not going to do this all the time. What you want to do when you talk about objects on ramps is imagine that we are looking at it this way. Imagine that that arrow that I drew, which isn't really vertical, is vertical. So we are always going to want to analyze forces in, and I'm going to draw something here, it's just me drawing and I'm going to erase it very quickly. We're going to want to analyze forces that act either in this direction, or this direction, or this direction, or that direction. Because the two arrows along the ramp show the directions the object could move, and the other two arrows show normal forces and some force that balances the normal force. So that's kind of the setup for today, and I know that was a long-winded setup, but I think it's important that you understand where we're going with this. You may have gotten used to the fact that you use this formula to calculate force due to friction. But again, you can only get away with that if it's on a horizontal surface. So now let's wade into the lesson. The warm-up says we want to sketch a diagram showing a 12 kilogram mass at rest on an inclined plane when the angle of the plane is 30 degrees. And whenever we see the angle given like that, it means 30 degrees to the horizontal. So you're going to take a second here. If you have a ruler, that's even better, but you don't have to have a ruler. We are going to be drawing a ramp, inclined plane, whatever you'd like to call it. It doesn't really matter which way you draw it. I'm going to draw it this way, but I could draw it the other way. It appears as though, we don't know why, they've done research on this, people seem to understand these problems better if we draw the ramp going up to the right, and nobody seems to understand why. It's just the way the brain works. Now we also have to draw some kind of an object on there. Of course, we typically draw this as the classic box. And I can never quite get it exactly right, but that doesn't matter. So we have this situation, and it says that there's a coefficient of friction of 0.75. So what I want you to understand here, probably before we get going with this, is if that block is made of oak and that ramp is made of cedar, then the coefficient of friction is 0.75 no matter how steep the ramp is. That 0.75 for mu is an actual property of the surfaces. So mu equals 0.75 would still be 0.75 if the object were on a horizontal surface. Can you guys still hear me?
Yeah.
Thank you. The only reason I asked is I'm looking at my little icon up there and I can't see volume coming out of my icon when I talk, and normally when I talk it does. Can you hear me well?
Yeah.
Okay, I'm just checking. Must be just a little glitch in Google. So, we've got this situation, so we've drawn it. I mean, I don't know that we need to really label anything. It's a 12 kilogram mass. I guess we could put 12 kilograms on there. We could label the angle as 30 degrees. By the way, we know that it's a 90-degree angle over here. And I've got the coefficient of friction written down as well. So now we're asked to draw a free body diagram showing the forces that act parallel to the plane and perpendicular to the plane. So I don't want you to draw anything just yet, and this is a little hard to follow without having a ramp in front of us where we would do a couple of demos. I hope you would understand that the force of gravity, and you're not drawing this, the force of gravity does in fact act on this box downward. No question about it. Gravity is towards the center of the Earth. But the gravitational force is actually doing two things to this box. What the gravitational force is doing is pulling the box against the ramp, perpendicular to the ramp. So I hope you would agree that if you were to be laying on the ramp and I put a 12 kilogram box on top of your stomach, you would feel it pushing against the ramp. So the gravitational force is doing two things. Even though it's really pulling down, it's pushing the box against the ramp, but it is also causing the box to experience a force towards the bottom of the ramp. And I'm going to align these vectors in a slightly different way in a second. Actually, I'll do it right now. That this force here, and you're not drawing this. I'm going to get rid of this 12 kilograms just for a second. This force, which is the true force of gravity, okay? It's the actual force of gravity, results in pulling the box along the ramp and pulling the box against the ramp. And those two forces that I've drawn, if you were to draw them tip to tail, those two forces, the force of gravity pushing against the ramp and the force of gravity pulling along the ramp, when you add them together, you get the force of gravity. So we are not asked to draw a true free body diagram. We're asked to draw a free body diagram showing the forces that act parallel to the plane and perpendicular to the plane. So now we're going to start drawing things. What we are going to draw, we're not going to use this force of gravity. We're going to draw these two forces. So those are the two forces acting perpendicular to the plane and parallel to the plane. And what we call the perpendicular force is the force due to gravity that is perpendicular to the plane. And what we call the force that is acting parallel to the plane is the force due to gravity that is parallel to the plane. So we have Fg parallel, and we have Fg, I'm going to rewrite that just to clear it up a bit, and we have Fg perpendicular. So those two forces that we've drawn, or that you're just finishing drawing, are the parallel and perpendicular components of the true force of gravity. The true force of gravity is acting down. And now we start to get a handle on something because, and let's just assume that the box isn't sliding, and in fact it isn't. It's not sliding, it's at rest. And we're going to say it's at rest because there's just too much friction. If it's at rest, that means the forces must be balanced. And if the forces are balanced, there must be a force exactly equal to the perpendicular component of gravity, and it must be acting in the opposite direction. And there must be a force exactly equal to the parallel component of gravity, but it must be acting in the opposite direction. I want that to sink in, that the force due to gravity causes this force to exist, which we call a parallel component due to gravity, and it causes this force to exist, which we call the perpendicular component. But the box doesn't move. The box is experiencing, if it's at rest, an acceleration that's equal to 0. And if the acceleration is equal to 0, then according to Newton's second law of motion, the net force is equal to 0. And if the net force is equal to 0, all the forces balance. So this force that I've drawn opposite to the perpendicular component of gravity, this force must be exactly equal to the perpendicular component of gravity. And this force, which is backwards towards the top of the ramp, must be exactly equal to the force of gravity acting parallel to the ramp. But let's label what these forces are. This is the force of friction. This is the normal force. Now we want to be very, very careful here about drawing generalizations that may not always be true. What is always true for an object on a ramp is that the normal force is not equal to the force due to gravity perpendicular. Looking at that diagram, I'm talking about the two forces I've highlighted in green, but the magnitude of the normal force is equal to the magnitude of the force due to gravity that acts perpendicular to the ramp. The fact that the force due to gravity parallel to the ramp is equal in magnitude to the force of friction, the fact that the two blue vectors are equal and opposite, is only because it's at rest. If it were accelerating, that may not be the case. If it were accelerating, then maybe the force due to gravity parallel is greater, and that's why it accelerates, because it's slipping. And now we come back to the basic idea here. We've drawn the free body diagram, determine the normal force acting between the mass and the plane. Well, this is the same as what we did last week. We do not have a direct way to calculate this force. I'll highlight it so you know what I'm pointing at. We are asked in question 3, calculate the normal force. We don't have a way to do that. but we do know that the normal force is equal in magnitude to the force of gravity perpendicular. We do know that that force we're asked to find in question 3 is this. So that's what we're going to do. For an object on a ramp, what I'm about to write is always true. The magnitude of the normal force can be found by calculating the magnitude of the force of gravity acting parallel or perpendicular to the ramp. So how do we do that? I'm going to redraw this, and I think it might not be a bad idea for you to redraw it as well. And the reason I'm going to redraw this is because I'm going to draw the force of gravity on it, the true force of gravity, and I'm going to draw the parallel and perpendicular components as well, but I'm going to draw them together. So let me, before you actually draw in these forces, let me do this, and then I'm going to move some vectors around. We know that the force due to gravity does act downward. That's true. And we know that we can think of the force due to gravity as being a force pushing it along against the surface and along the ramp. But we also know, and this is where you're going to start thinking about how to draw this, we also know that these two red vectors, drawn tip to tail, give you the true force of gravity. My computer is not very responsive this morning. I'm sorry about that. Got some issues here with my mouse, maybe. Oh, yeah. Move that off screen. So what we're dealing with here, everybody, is that this force downward is actually the force due to gravity, whereas this force that I've got down here is the force of gravity component that is parallel to the ramp, and this is the force of gravity component that is perpendicular to the ramp. And don't forget, in this question, we are trying to find the perpendicular component of the force due to gravity because that's the normal force, which is what we are after. So how can we do that? Well, you need to understand something here, and I'm not going to get into a geometry lesson, but you need to understand that if the ramp has an angle of 30 degrees here, then this is going to be 30 degrees. So we're dealing with a right angle triangle because these two are perpendicular to each other, where the hypotenuse is the force due to gravity. And that means that if we want to find the perpendicular component, it is adjacent to the 30-degree angle. This is 30 degrees. So we can write cosine of 30 degrees is equal to the adjacent side, which is FG perpendicular, over the hypotenuse, which is FG. Now we calculate FG by using mass times 9.81. So I'm going to go back to my regular Zoom. So we calculate Fg by taking mass times 9.81. And we end up with this statement that cosine of 30 degrees is equal to the component of gravity that is perpendicular to the ramp over the mass. So this is mg. The mass, which was, I think, 12 kilograms. I better go back and look. 12 kilograms times 9.81 meters per second squared. So when we cross multiply the component of gravity that's perpendicular to the ramp we'll have a magnitude equal to 12 times 9.81 times cosine of 30 degrees. So take a minute, please, and calculate that. And hopefully you get 101.99485 newtons. Can anybody let me know if you get that same number? Okay, Andrea's got it. So that's a pretty basic calculation. I think we're in agreement. Let's just call it 102 newtons. And I really don't care about significant figures here, but I want to go back and answer the question. The normal force the magnitude of the normal force is equal to 102 newtons because the magnitude of the normal force is the same as the magnitude of the force of gravity perpendicular. So before we go on, let me cut to the chase here. What do you need to know? I started off this lesson by telling you that if the object is on a horizontal surface and we need to find the normal force for some reason, I'm looking at the left-hand side of this page. The normal force is found by calculating the force due to gravity. However, I said, what if the mass is on an inclined plane? How do we find the normal force? Well, what we have just learned is that the normal force is equal to the component of gravity that acts perpendicular to the ramp. So if you were writing this down as a nice summary between the two types of situations, what you can put now is that this is the force due to gravity acting perpendicular to the ramp. So the things in yellow are the things you need to know. And why would you need to be able to calculate the normal force for an object on an inclined plane? Well, because maybe you want to find the force of friction, and the formula for force of friction is mu Fn. So I'm going to pause there. I've done a lot of talking and a lot of explaining here for the setup for the rest of the lesson. So I want to make sure that it's sunk in, and I want to make sure that if you have questions, you get a chance to ask them. So does anybody have any questions regarding what we've just talked about, which is summarized nicely on your screen right now?
Mr. Wade, can you go back to the whole other thing? I didn't quite get all.
Okay, and that's the same with you, Taylor. I'm sorry. I jumped ahead too quick. We're talking about this, correct?
Yeah.
Okay. Sorry about that. This diagram, while you're finishing writing this down, this diagram that I have, I only put so that you could understand how we could calculate the perpendicular component. The fact of the matter is, when we draw the free body diagram, and you don't need to erase anything because this is drawn elsewhere, but when we draw the free body diagram, what we do is we say, I'm not going to draw the force of gravity. I'm not going to draw the 30 degrees. What I'm going to do is draw the force of gravity perpendicular and the force of gravity parallel on the object. So this that you're looking at now is how you would typically draw the two forces. What I had before is what you would have to draw if you needed to figure out how to calculate them. But this diagram you will never have to draw again. So can I move forward now? Any objections to me moving forward? You got it all copied down? Okay. Determine the magnitude, and remember what I said, you're not going to have to draw that anymore. So what's the magnitude of the force due to friction? Well, the magnitude of the force due to friction is found by using your formula from the formula sheet. This is always how you calculate the magnitude of the force due to friction. Now, if this were on a horizontal surface, the normal force would be Fn. But we've just calculated the normal force to have a magnitude. Can somebody verify this for me that it was 101.9, so 102 newtons? Okay, thank you, Andrea. So what we're going to do is we're going to put mu in, and mu, I remember, was 0.75, so it's 0.75 multiplied by 102 newtons, which was the normal force. And what we're going to get is 76.5 roughly, but yeah, 76.5 newtons. So does anybody have any questions with number 4? All right, so the reason I told you that you don't have to draw this diagram anymore is because we made a decision in the science department at WCHS that what is important is the force analysis, not how to find these components of force, because the force analyses will be getting more and more complicated. So even though the formulas that you're looking at in the next section in your handout are not on your formula sheet, we give them to you for exams. So the next example, well, the first example, a 12 kilogram mass is on an inclined plane that makes an angle of 64 degrees to the horizontal. If the coefficient of friction is 0.62, what's the force of friction? So we go to our formula sheet and we see that the force due to friction has a magnitude of mu times the normal force, but we say, this is you, this is me. We're asked in example 1 to find the force due to friction. And by the way, whenever you're asked about the force due to friction, it's the magnitude. We don't care about the direction. We'll worry about the direction later. So there's your formula, but then what you have to do is say to yourself, what is the means by which I find the normal force? Because there's no way to calculate it directly. But you say to yourself, that you remember on an inclined plane, the magnitude of the normal force is exactly equal to the magnitude of the force due to gravity. And I can put that perpendicular symbol outside or inside of the absolute value signs. It doesn't matter. Now there's 2 ways to proceed here. I'm going to show you what I would prefer to do. I would prefer to look at my formula for FG perpendicular, which is Fg multiplied by cosine of theta. Just make sure. Yep. And then I would say that Fg is mass times g. So what I develop kind of in my head is that Fg perpendicular is mg cos theta, and then I do the following. Then I have a formula which says the magnitude of the force of friction is mu mg cosine theta. If you want, you can use this formula up top to calculate this as a certain number of newtons and then put it in here. But there are going to be problems that you will encounter sooner or later that require this substitution method. This is a better approach. So now I can put in mu, which is 0.62, the mass, which is 12 kilograms, Are the numbers in my question the same as the numbers in yours? Thank you, Andrea. And then times 9.81 meters per second squared, and then multiplied by cosine of 64, and we are going to have our answer. .62 times 12 multiplied by 9.81 multiplied by cosine of 64. 0.62, 12, looks okay. What we get is a force due to friction of 32 newtons. So the magnitude of the force of friction is 32 newtons. Now, so I'm going to stop there. Any questions with that calculation? What I would like everybody to do right now for example 1, even though we weren't asked about this, is I would like everybody to calculate this, the force due to gravity parallel to the ramp. It would be mg times sine of theta. So it would be 12 times 9.81 times sine of 64. I want to throw this out to you because sooner or later we're going to have to grapple with it. And I think you know me as a teacher by now. Rather than letting it all pile up and giving it to you all at once, I like to have things that we can refer to later. So if I take 12 times 9.81 times sine of 64, I get 106 newtons. And the question I want to ask everybody, which isn't part of today's lesson, but I'm throwing it out there anyway. This 106 newtons is the force of gravity that is pulling the object along the ramp towards the bottom of the ramp. So if I draw this, I won't waste a lot of time with this, I'll just roughly draw it. It's 64 degrees, so it's quite steep. Here's the box. The force due to gravity down the ramp is 106 newtons. My question to you is this: will the box slide down the ramp? And why or why not? So gravity is pulling the box towards the bottom of the ramp, parallel to the ramp with 106 newtons. And my question is the box going to move? Taylor says yes. That's correct. The box will move. And Andrea adds to that, yes, because the force of friction is smaller. The force of friction is the only force opposing that motion. So the force of friction is only 32 newtons, which is a little piddly kind of thing here in the opposite direction. I got 106 JV by calculating the force of gravity parallel to the ramp. This is not part of the question. It was just something I wanted to do to open up a discussion about forces. So can anybody else, before we go on with this, confirm that it is 106 newtons for the parallel component of gravity? Okay. So this JV, this 106 newtons is not part of the question. We're done with the question as soon as we got that 32 newtons for a force of friction. But I'm just kind of using this to expand on forces a bit. So we calculated it to be 106 newtons. This is the force of gravity parallel to the ramp. And remember, the force of gravity parallel to the ramp is the force of gravity acting towards the bottom of the ramp. And I had told you that these two blue vectors you're looking at now are not always equal. They are if the object is at rest. But what Andrea and Taylor correctly pointed out here was that if we get 106 newtons for a parallel component towards the bottom of the ramp, but we've calculated the force of friction to be 32, there's a greater force down the ramp than the opposing force of friction, so it will accelerate. If I asked you now, and I'm really pushing it, I agree, but I ask you now to calculate the net force on the box, I want everybody to look at that diagram that I've got here. Know, of course, that there is a perpendicular component of gravity that is balanced by the normal force. I want you to calculate the net force. I want everybody to see if you can figure out what the net force acting on that box is. And while you're thinking and working, I will throw a hint out to you, and that's that net means total. So I'm asking you, what's the total force acting on that box? Now, Mackenzie, are you saying negative because it's down the ramp? Okay, so, and that's my mistake. I should have said, what's the magnitude of the net force? Since we've got directions here that are not left, right, up, down, we don't use positives or negatives here. So what we would just say is that the net force is 74 newtons down the ramp. Now, can you type briefly how you got 74? Right. We know from way back when, I mean, I don't know when that was, that when, and the other forces cancel exactly. So this force and this force added together give you nothing. And we've learned that when you add forces that are in opposite directions, which the 106 newtons and the 32 newtons are, that you subtract the numbers, and then the answer is in that direction. So the net force is 74 newtons. From that, you could find the acceleration by dividing by the mass, because F net equals ma. All right, let's move on. A 6 kilogram mass is on an inclined plane that makes an angle of 38 degrees to the horizontal, and there's a force of friction of 20 newtons. So I guess we start, and I'm showing this to you from a standpoint of a written response assignment. We start with a formula on the formula sheet. Then we say on an incline, the normal force is equal in magnitude to the force due to gravity acting perpendicular to the ramp. And again, where you put that perpendicular sign is up to you, which is the force of gravity times the cosine of theta, which is mg cos theta, and then you put it in. You go FF equals mu mg cos theta. What I'm telling you, and it's just the way it is, you guys, is you cannot start on a written response question by writing this. You can memorize it, but that's not your starting point. If you write that as the only formula you use, that is a formula that's not on your formula sheet, so you need to explain where it comes from. Okay, let's put the numbers in. The force of friction is 20 newtons, so we have 20 newtons equals mu, which we do not know, times the mass, which is 6 kilograms, times 9.81, times cosine of 38 degrees. I would recommend at this level you calculating what this is to get a simple equation. So 6 multiplied by 9.81 multiplied by cosine of 38 gives me 46.38. I, well, I was debating there on whether to put the newtons. The 20 is newtons, the 46.38 is newtons, so when we divide them, we're going to get a pure, what we call in science a pure number, a number without units. So I have to take 20 divided by 46.38. Which gives me mu equals 0.43. Any questions with that example? Okay. Now, I want to go back. I know this seems like it goes on and on and on and it never ends, but I want to go back to this. And I guess I'll present it as a full page. It'll start to get narrower because I'm going to add something now. What we have discovered is that if it's on a horizontal surface, we can use this formula. The magnitude of the force of friction is mu mg. Because if it's on a horizontal surface, the normal force is the force of gravity. However, what we've discovered, and you would have to explain where this comes from on a written assignment, on an incline it's mu mg cosine theta. I hope you're with me on that. That's what I suppose we can memorize. That's the result of analyzing the forces. And by the way, I suppose I could add on to this diagram now, and then later on I will leave this up and you can take a screen capture or a picture of it. I guess I can label the forces a little bit more clearly now because now you know what they're called. This is the normal force. This is the force due to gravity that is perpendicular to the ramp. We also have a force of friction, and we have a force of gravity parallel to the ramp, and I'm going to discuss the lengths of those in a second. So this is the force of friction, and this is the force of gravity parallel to the ramp. What we don't have are other forces that maybe somebody is pulling or pushing on the box. I'm going to just pause here. There's so much going on, but I want everybody to look at the diagram I drew for the mass on the inclined plane, and the question I want to throw your way is, will the box move? So Andrea thinks no. Sienna thinks no. Sienna, can you tell us why you think the box won't move? You're right. It will not move. Right, the force of friction is bigger than the force of gravity parallel. By the way, some people will look at that and say that the force of friction is bigger so it will move up. That just doesn't work. So the force of friction is larger. If the force of gravity parallel to the ramp is bigger than the force of friction, yeah, it's going to move. If the force of gravity is smaller because the force of friction is larger, it won't. But I want to get back to an interesting point here that's going to be very helpful for some of you. When you think of this, I'll highlight it. When you think of the surface of this ramp, which is right here, the angle is theta. When you think of the surface of this on the left, I want everybody to think about what the angle between that surface on the left is and the horizontal. How many degrees is it between that on the left and the horizontal? It's 0, right? Theta is 0 degrees over here. Theta is 0 degrees. Okay, let's try something. What if we put cos theta on this one as well? What if we could use the same formula whether it's on a ramp or it's not? Well, I would like you to figure out what cosine of 0 degrees is. It's 1. Which means we're going to have mu times m times g times 1, which is mu mg, which is the formula we developed. So what I'm telling you is you could use, just to memorize it, mu mg cos theta all the time. All the time you could use that. But you do need to know how to get the formula that you're going to be using on a written question. So I'm going to give you guys some time here to work on some of these questions. There's not a lot, right? There's only 3, is that right? Yeah, pretty sure there's only 3. So I'm going to give you guys about 15 minutes to work on these questions, and then we're going to move on and look at one application of Newton's second law dealing with vertical motion. If you do have a question, please let me know, unmute your mic or type something in the chat.